sound in the lab, Twitch stream glowing, formulas flashing, minds wide, knowledge flowing, equations on the board, numbers never sleep, teaching math and physics while them haters count sheep. Actual education, tune in and get schooled, flipping textbooks, breaking all the rules, from Newton to Einstein, concepts elevate. Keep the stream, it's the key to our fate. Dr. Gold dropping gems, knowledge raining down, actual education making scholars all around. Perpendicular minds, angles sharp as ice, maths and physics, yeah, the future's real nice. Got the Pythagorean triangles about to flex, quantum theories on deck, breaking all the specs, relativity theories, worlds getting small, grasp the universal laws, standing tall. From the atom to the cosmos, we rolling deep, grazing up the stars, no time to sleep. Black holes and supernovas, concepts we unfold, brain power heavy, yeah, that's Dr. Gold. Dr. Gold dropping gems, knowledge raining down, actual education making scholars all around. Perpendicular minds, angles sharp as ice, maths and physics, yeah, the future's real nice.
Alright, there we go. Let's see. Boom, boom, boom. Share. Nice.
Hello.
What's up, Emily? How's it going?
Hi, I'm doing good. How are you?
I'm good. Let's see. Oh, I think you sent me an email about missing your homework or something. Sorry, I'm
Yeah.
getting so many emails today. I promise I'll get to all of them, but like, oh my god, so many emails.
Yeah, no worries. Like, I just wanted to ask about one of the homework problems.
All right, let's do it. Here, let me put this away. Okay. Which one did you need help with?
Should I share my screen?
I don't think it'll let you on that. You can just tell me which. You can tell me which homework question it is.
Okay,
It's in
so
which
it's
section?
It's the fluid mechanics homework.
Yes. Okay.
It's the one about the automobile hydraulic system.
Okay, perfect. Okay, this one. Question 1.
Yeah.
Okay. All right, let's pull it up. Sorry, remove all this. What's up, Cusick? All right. Let me delete all this. Okay, cool. All right. Consider the automobile shown. Suppose a force of 100 newtons is applied to the brake pedal, which acts on the pedal cylinder, acting as the master cylinder. Okay. A force of 500 newtons it's exerted on the pedal cylinder. Okay. Oh, I think like there's some extra information here. Yeah. So they tell us that this is 100 newtons, which is like cool. But then they tell us that 500 newtons is exerted on the pressure. This is the pedal cylinder. So this is going to be 500 newtons. And the reason why that is, I think has to do with torque. Wait, this is, let's see, one sec. Yeah. Okay. I guess cause okay. Let's see. Pressure created in the pedal and the cylinder is transmitted to 4 wheel cylinders. The pedal cylinder has a diameter of that, and each wheel cylinder has a diameter of that. How much pressure is transmitted in the hydraulic system? Express your answer in atmospheres. Okay. Well, in hydraulics, pressure is constant. The only thing that changes is like force over area. So we say like P1 equals P2. The difference is F1 or A1 is equal to F2 over A2. So if the pedal cylinder has a diameter of that, each wheel cylinder, and then there's 4 wheel cylinders, right? There's 4 of these. So A2 is going to end up equaling 4, and then that's going to be times pi times the radius, but they gave us the diameter of that, didn't they? Yeah, that's the diameter. So this and this is 1.25 times 10 to the minus 2 squared. Okay, so that's the area of the total for the wheel cylinders.
So you can just treat all the areas as like one?
Yes. Yeah.
Okay.
If you have a hydraulic system like this, and then you end up having like a couple of these that are connected, you can treat this as a single one that has twice the area.
Okay.
Okay. And then it should have, so this has 4 of them, so that's why I do 4 times pi times that. Okay. And then that needs to equal the same thing here. So the same amount of force that's going in, which that's 500 newtons. So F1 is equal to 500 newtons. And then let's figure out what A1 would be. A1 is a single cylinder, which has a diameter of 0.5 centimeter. Okay, so that's going to be pi times 0.025, or no, so 0.25 times 10 to the minus 2 squared. Because this is still, yeah, this is in centimeters. Yeah. Okay. And then I think all you're doing is you're just doing this over this has to equal this divided by this.
Okay. Wait, so like what does the question mean when it's asking for like the pressure that's transferred?
Oh, okay. How much pressure is transmitted?
Transmitted.
Oh, okay. Oh, then I think you just need this. Because pressure equals pressure is what it should be. Pressure here should equal pressure here. Usually what they ask is like how much force is being exerted. I was just setting it up, but I think they just literally want this. Let's see if it's right.
Oh, okay.
I can check. I remember this question being kind of weird. Because they give you a lot of extra information on this one.
Yeah, I was just confused by the diagram.
Yeah, the diagram sucks too, honestly.
You're not that guy, pal. Trust me. You're not that
The
guy.
diagram sucks. Okay. Yes, you're right, Ryan. It only asks for the pressure. Yeah, sorry. Now I'm reading the chat. Okay, cool. All right, so if you did, was it 500? Because usually the next question is like how much force is exerted on each of the pedals. That's usually what you're supposed to answer. This is times 0.25 e minus 2. Oh, but then this needs to be squared. Okay, cool. So that gives us a ridiculously large number. Okay. And then I think so the answer choices were all in atmospheres, right?
Yeah.
Yeah. So if they're all in atmospheres, you have to remember, do you remember how many pascals are in an atmosphere?
Like 101,000.
Good. Yeah, 101.3, times 10 to the 3. Yeah, because it's kilopascals. Okay, so see if that's right. So if you divide that by 101.3 e to the 3, then that gets you 251. 251 atmospheres, which I think was the correct answer. Yeah, because if we look here at Kudu, yeah.
Okay.
It was 251. Oh, well, this is... Oh, my God.
Can I just ask like a few more questions like
Of
about
course.
the diagram?
Yeah, of course. Yeah. Ask. So this... I will admit that when this the way this question was like drawn and written, I instantly defaulted towards solving for the force because that's what it looks like it should be asking for, but because they give all this information and all these things, but at the end of the day, they actually really just wanted the pressure. Yeah. But anyways, what do you want to ask about the diagram? So please. Yeah.
So like when you calculate F2, like you did below.
Yes.
So will all four of the F2 forces like shown in the diagram, will
Will all be
those
the same.
those will all be the same as like if you calculated the area as like one total area? Like you Oh, okay. So it's not like you have to do like each one like separately, right?
No, because these four together act like a single cylinder that has the same force at every like location. Like this F2 equals this F2 equals this F2 equals this F2, okay? But it's for this whole, you would say like 4A2, I guess, right?
Yeah. Okay. Okay, that makes sense. Yeah. And then the F1 like on the left is just the
This is 500.
500 newtons.
Yeah, so this right here is like extra information. They're kind of just messing with you. And I think where this comes from is it comes from torque. So if you're applying like 100 newtons on a pivot here, right? Then I think that equates to 500 newtons getting applied right here.
Okay.
That has to do with, if you remember from torque, right? So torque is equal to R cross F.
Yeah.
Yeah.
Okay. Okay, yeah, that makes sense now. Yeah.
Because I think this is a ratio of 5 is what this is. So applying 100 newtons here is like applying 500 newtons there.
Okay. Okay, that makes sense.
Yeah. But you didn't have to know that. They gave that to you.
Okay. All right. Thank you.
All right, you're welcome. I apologize. This question was like kind of honestly bullshit. Kind of just use the ones they give us to us. All right. Any other questions for you guys about different problems here?
Yeah, I have just like a list of like quick questions.
Let's do it, Jack. What's up?
For chapter 1 with fluid dynamics.
Yes.
So of course we have to memorize like the density of water being 1,000 kilograms over meter cubed. Are there any other densities we need to know by heart?
No. Any other densities like that would be given to you. The 1,000 is just like a nice number you should know in your head just for water. It's pretty good.
In the notes there was something called specific gravity. Do we need to know that?
Oh, specific gravity. Yeah, that's used for, let me see. Where did they put that? Specific gravity. One sec. I think that has to do something for... Yeah, here we go. Okay. Yes, that's for when you're comparing densities between things. But you can do that knowing the density. I see. Yeah. Specific gravity is for if you have like two materials of different densities that are like in the same container, it's a way to figure out like what the heights would be and then where things are. But you can just use density. Yeah, you don't have to use specific gravity.
Okay, that's good to know.
Yeah.
All right, so I have another question.
No, you're good.
Give me a second.
Rattle them off.
Do I need to know the variation of atmospheric pressure with height? If there's like a whole little like section.
Oh, this one. No.
Okay.
Yeah. You should know like how pressure varies in a fluid with the height of the fluid. But yeah, no, in terms of like in the atmosphere, no, you don't have to do that. You don't have to know.
Okay. For units of pressure, what conversion factors do I need to like know by heart? Because I know 1,000 MV equals 1 times 10 to the 5 pascals.
Yeah. So this is a very useful one, right? The other one that's useful is 760 millimeters of mercury, that's also equal to 1 atmosphere. And I think this is also called 760 like torr. These are also useful ones to know.
All right.
I'm trying to think if there's anything else. Yeah, no. And a lot of times we'll deal with just Pascals. This homework question, for example, they wanted atmospheres, but yeah, this is the conversion you want to know.
Okay, do I need to worry about hydrostatic equilibrium? Like, I just know when that's just referring to when a water is in equilibrium. So it's not that hard to remember.
Yeah, I mean, that occurs. Hydrostatic equilibrium means when everything's like kind of just still, right? Hydrostatic. 1 sec.
Hydrostatic is like for a fluid when the fluid is water specifically.
Oh, I see. Yes.
I guess it's
Yeah.
just like a vocabulary word.
Yeah. They throw out like all these like little terms here and stuff for things. I'm not. This isn't an English class. I'm not going to test you on like vocabulary stuff.
Okay.
As long as you can use it. Yeah.
All right. Give me another second.
You're good.
Are there any for flow rate and like relation to velocity? Do I need to worry about like any other like conversion factors? Because I know like the unit for flow rate is like meters cubed per second,
Mm-hmm.
but you also have like liters per second. So I'm like,
Oh. Well, so that's flow rate, right? Q. That's equal to, I think that's A1 times, it's A times V, right? This is where this is going to be, this is meters squared, right?
yeah.
And then this is just, and then this is meters per second. Yeah. And then is there a density? No, there's not a density in this. It's just A1. Yeah. Because you assume it's the same fluid. So whenever you're doing these questions of, for instance, having fluid that's running through one container, and then it like maybe gets funneled down into like a narrower container. Yeah, you actually don't. The other thing I was thinking about is called mass flow rate, or mass flow rate would be like kilograms and then like meters per second. You've maybe seen this one in calculus before. They'll say like mass flow, and that's kilograms times meters per second. But in this case, we assume that the fluid in one situation and then the other situation, it's the same fluid. So it actually cancels out when doing this continuity equation.
Okay. And my last question is, so Bernoulli's equation is only usable when the fluid is inviscid, basically no friction.
Is that like incompressible? Is that what they say?
Yeah, incompressible and in
Yes.
steady flow. So
Yes.
if we have a situation where one of these is not true, can we not use Bernoulli's principle?
Correct.
Because the energy goes in and out of the system. And it's
Yeah.
not
Because you have non-conservative forces in that case. There's like almost like a friction within the fluid.
So like the total pressure is conserved, but like pressure 1 doesn't necessarily have to equal pressure 2.
Correct.
Right.
Yeah. Or total pressure, yeah. But it for all the questions that we've done here and all the questions you'll do on a test and everything, we're gonna assume that you have an incompressible fluid. Yeah.
Okay. Then those are all my questions. Thank you very much.
You're very welcome, Jack. Cool.
I had a question for one
What's
of
up,
the
Ryan?
proposals. Yeah, it's the homework problem, question 8, part B on periodic motion.
All right, let me go find it. Periodic motion. Question 8. Let's see, question. Let me go find question 8. Oh, this is the toddler. Yeah.
Yeah, I did the question myself, and so it was wrong, and I checked online, and
Yeah.
I also got the same answer, so like AI, so yeah. So I'm not,
So yeah, let's see if something's wrong. So part B of the toddler one, is that what it is?
yeah, part B.
Okay. And And then interesting, I can't even see what the correct answer is on that. Wait, what the hell? Oh, kudu. God damn it. Oh, wait. Okay, wait. I have... Oh, this is a bug. Because there is no correct answer? Wait a minute. Wait, that one's fine.
Someone on Campus Fire said they were able to like get credit for it, so but I guess I'm not that lucky.
Yeah, but I'm looking at it. I can't even put numbers in.
Oh, okay.
I'm clicking. I'm like, wait, where the hell's the numbers? One second. Let me sign in on my other student account. I just want to see what that says. Yeah, that's yeah. There we go. Let's see that. Okay, and then this was periodic motion. That's question 8. Question 8. Oh, I see. Okay. I can put numbers in on the student account, I see, but I can't on my instructor version, I can't see any answers for it. Which is weird. Okay. Do you want to just like see what it is and just like make sure we're doing it correctly, I guess, at least?
Yeah.
Let's do that. Okay. Because I think this is some of these questions have what's called like a random component to it, which means one of the numbers is gonna change. So for instance, in my version, the toddler has a mass of 14.2 kilograms, and then the stiffness on the spring is 857. But your version probably has different numbers, right?
Yeah. I sent
you have 10.1 and 822. Yeah. Okay. Okay, gotcha. Alright, let's see. So, part A was what is the toddler learns to bounce with a maximum amplitude and minimum effort by bending her knees at a certain frequency. What frequencies? This is just omega is equal to square root of k over m, right?
Yeah.
Good, okay. So, and then if you want the frequency for that, that's omega over 2 pi, right?
Mm-hmm.
Okay. So let me see. I see on my student side. Did part A go correctly, but part B didn't?
Yeah, part A went correctly, yeah, but part B,
Okay.
I can't get it.
All right, let me see. Let me check that. All right. Let's see. Square root of, and that's gonna be 718. I want to see if mine's 718 over 16.9. Okay, that's omega, and I'm going to divide that by 2 pi. So I should have gotten 1.03. Let me see if I get that right. Okay, so part A I got correct using just that. Okay, it says when can the toddler use the mattress as a trampoline, losing contact with it for part of each bounce? Give the minimum amplitude. Assume that, okay. This happens when the maximum acceleration of the mattress becomes greater than the acceleration due to gravity, so that the top of the bounce, the mattress starts moving down faster. Oh, okay. And then when? Oh, the minimum amplitude of bouncing for this to be the case. Okay. where is amplitude for bouncing? Okay, maximum acceleration is omega squared a, I think, right?
I think it's. Oh yeah, it is. Yeah.
Is it omega squared a? I'm pretty sure it is because you pull out an omega when you do derivative once, right? So you have, what is it? A.
Yeah, that's for max velocity. Yeah.
Good, right, okay, yeah. It's like omega t. Yeah, so this is position, so then velocity is a omega cosine omega t. And then so acceleration is going to be a omega squared. Actually, technically there's a minus sign. Okay. And so they want to know when the maximum acceleration becomes greater than the acceleration due to gravity. So that's when a omega squared is bigger than 9.8, right?
Yeah.
Okay, cool. And then let me see. My omega was 1.0. Whoa, okay, wait. Okay, so 9.8 divided by k over m. That's all it should be, yeah? Let's see. Okay. I have that. I'm going to square it. That's k over m. We do 9.8 divided by that. And I should have gotten 0.23 for my answer. Yeah, and that marks is wrong. Interesting. Okay. And you did it this way, Ryan, right? You did 9.8 divided by k over m.
I have two ways, like,
Okay.
because, yeah, the first way I just did a force diagram, and I noted that the force, the force should be equal to the force of the spring displacement. It should be equal to the force of gravity, and then also your way that you just did right now. They both give the same answer, at least.
Yeah, but it's not, but the right number's not coming up. Yeah, because I see that on my end too. If I put in what I did for this, let me think. Is there anything else that's tricky on this? Oh, you know what might be interesting here? One sec. I can go in and like manually edit this question. Let me go see. Or I think I can. Maybe not if it's already released. One sec. It was periodic motion. It was question 8. Yeah. Let me go through and edit question 8. Yeah, so I can see it right here that it should have been 9.8 over k over m. I can at least see it. Wait, where did this come up? Yeah, that's a bug on their side. I think what's happening because there's supposed to be a random variable for each of those parts. That random variable should be changing, but it's not changing on the display. So you're not seeing what the new stiffness and the new mass is for you to do part B. I understand that.
I see.
Yeah, so what's supposed to happen is if you have like a random component to the question, again, this is not your fault at all. This is not physics. This is just development stuff. It's because it's not displaying what the new number is. All right, that's a bug. I gotta tell them that. Okay, let me make a note to myself to do that.
Yeah, there's like 3 posts on Campus Wire, so about the same questions.
About the same one. Let me just pull it up.
Yeah.
Okay. Where was it? I think it was. If we type in like periodic motion.
this week homework question, and I remember the question last week. It was just called homework question.
Oh, okay. Or is it? Oh, the man. Maybe baby. No. I gotta go find where it was though.
I also posted in chat.
Oh, you did? Oh, thank you so much,
Yeah.
Ryan. Oh yeah, that helps. That helps me immensely. Okay, cool. Also, why is this kudu thing displaying? What the hell? One sec. Why is that over there? There we go. Okay, good. Yes. Okay, here. I will answer this question then. I'll be like, this is a bug in. This is a kudu bug. Because set of random numbers should show for part B, but they're not. Everyone credit for this. You're correct.
I also posted the other campus fire link with the same question, but
Okay.
different names.
Cool. And then what do we do? Was it MG over K? Yeah, MG over K. Okay, cool. Thanks. And then that's the other one. Yeah, cool. Okay. Okay, cool. Thank you. Yes, that is a bug there. Let me put that on. There's a big spreadsheet they gave me of all the things they're trying to fix. And I was like, yeah, here guys. Add this one to the list. Here we're gonna say on let me see. On a multi-part what's this gonna mean? Numerical question with random variables. Part B, part A works fine, but part B does not. It's not. I think it's because cool. And let me pull the screenshot for that. And then this was question 8. Sec. Yes. Okay, cool. All right. I'll get that fixed. Thanks for pointing that out. I'll make an announcement. I'll just give everyone credit for that question, but you did it the correct way.
All right, thanks.
Cool.
I had another question.
Yeah, what's up, Ben?
Can you explain fluid mechanics number 10?
Yes. Of course. Ryan, do they not use AI to vibe fix everything? Dude, this is also a great display of why using AI to coach stuff is like kind of terrible. I think what they did do is, so Kudu's been rock solid, working pretty well for like probably the last like 5 years. I've used it for a lot of my classes, and then this year with all like the vibe coding like hype. They're like, oh, let's just rewrite the whole thing using AI. And I was like, oh no, here we go. And we are seeing right now why that's a problem. Okay. Sorry, Emily. Which one? It was in fluid mechanics. Which question?
Number 10.
All right, let's do it. Luckily, physics doesn't change because of AI vibe coding. So, you know, we can still learn physics. But I agree. Trust me, I am frustrated that this is causing such headaches for me to like try to. Okay, here we go. Cool. All right. Suppose you measure a standing person's blood pressure by placing the cuff on his leg 0.5 meters below the heart. Calculate the pressure you'd observe if the pressure at the heart were 120/80. Assume there is no loss of pressure due to resistance. Density of blood is that. What does 120/80 even mean? Sorry, what? Oh, is that just like a fraction?
No, like, I had to, like, research what blood pressure units mean.
Dude, same. I'm like, wait, what? What is 120? Do they put that in the chapter?
No, I don't
No?
think so. But
You
it's
don't
not
think
it's not a fraction, I think.
Yeah. Oh, here you go. Oh, it's artery versus vein, systolic versus diastolic. Oh, okay. 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 Out from the heart, back for the heart. Okay. Oh, I see. Okay, so I think 120 is millimeters of Hg. That's the pressure at the artery, right? And so that's at the heart. So I'll say like heart. So this is 120 millimeters of Hg. And then you're measuring something located 0.5 meters below, right? So that should register I think a higher pressure because you have more fluid above it, right? Yeah, this should just be rho GH. So pressure should just be rho GH due to that amount of fluid that's above. And so that's the density, so 1060 times 9.8 times the height, so 0.5. Okay. Let's see what we're gonna get from that. So 1060 times 9.8 times 0.5. So that's 5194. And that's in pascals. But I think everything they wanted was in millimeters of Hg, right? So then you have to do the conversion that 101.3 times 10 to the 3 pascals is 760 millimeters of Hg. That's the torr thing. Okay, so let's divide that by 101. Oh, I guess technically, yeah, inches? Oh, no, we don't need to deal with inches. All right, e to the 3. Oh, come on, stop. Okay, times 760. So that's 38.97. Okay, so that's the pressure due to the liquid, due to the blood. But I think you have to add what the pressure is at the heart as well on top of it. So I think you would add the 120 to that. So this is just from the blood. And then the heart is already at 120. That's kind of like your P naught. Usually, whenever we're doing like Bernoulli stuff, like this would be like P atmospheric. So I think it should be 158. So let's see. Is that what the answer was? Go find it. Blood pressure. Yeah. Oh, it's super fascinating. Okay. I see it. So the correct answer was this is the correct answer here, M. 159 over 119. And so where that came from is, so the base pressure at the heart was 120 in the veins and 80 in the arteries. So then if you add the pressure due to the liquid, you end up adding 38.97. So it adds, yeah, basically 39 to each. And this is where you get 158.97, which is basically 159. And then this becomes 119.
Okay. But like, would the velocity like changing, like, would that like affect anything? Like these equation?
So they would need to tell us what the velocity of the blood was.
So we're just assuming it's like the same, like in
Yeah, you're assuming the blood is moving at the same velocity in the heart as it is 0.5 meters below the heart. If they don't give you things, you can usually assume that it's constant in physics. So we would say that, yeah, the velocity of the blood at the heart and the velocity where you're measuring, that should be the same.
Okay.
Yeah.
Okay.
I agree it's weird they gave you a fraction, but I get it. That's the systolic versus diastolic. Yeah.
Okay, that makes sense.
Yeah.
Thank you.
Okay, you're welcome. Bum, bum, bum. Yeah, that's a weird one. All right. Yeah. So that was more pressure questions we've been having. Now the students are starting. What did we do today? We did mechanical waves today. Yeah. Ugh. Let me read chat. Yes, Fenvox, I'm glad to see some of the students are coming to office hours. Yeah. It's week 2. Well, it's because things are due now. I think their first homework was due today at 2:00. Their second homework is due Wednesday at 2:00. So this is where all these assignments start kind of like piling on, and where it's useful to get help. And yeah, the questions are, a lot of them come from OpenStax. They're on this separate platform that the students use in order to like learn and do assessments, but a lot of it are a lot of the questions do come from OpenStax. Yeah. Yeah, we hope that the blood is a closed system for the most part in the heart. Otherwise, you're gonna have a bad time. But yeah, Gladiator, if you want to take a look at those, at like what we're going over, it's all in OpenStax. I think there's a link somewhere. Let's see. Yeah, I think a lot of it is here. Yeah. University physics. Let's see if we can find that exact question, because that was under... Not gravitation. Here, yeah. It was this. So if you go to problems, let's see if they come up. Yeah. So that's one we've done before. Oh, so it doesn't have the exact ones. But they're pretty related. Yeah, you found some? Okay, cool. Maybe they're in, sometimes it's in, like, additional problems. But yeah, we're starting basically with chapter 14. And then we're doing 15, 16, 17. And then we go into volume 2, which we do E&M. Yeah. Oh, I see. Yeah, you're right, Jeff. Yeah. It must have been volume 2. How do you like the OpenStack texts? I think they're okay. I mean, they're great for being free, for sure. I tend to like John Coley for physics, really. And I have the PDF of that one. That's the other one I use. I think, yeah, OpenStax is like, it's okay. I'd say it's mediocre. it does well for the price, for sure. And it's always getting improved. They're always putting more stuff on it, so it is getting better. Because it's open source. Yeah, John Coley. Yeah, I like John Coley. Let me find John Coley. What's up, Em? You have another question?
Yeah, I had another question.
Yeah, totally.
Number 20 on
Okay.
the fluid mechanics.
All right, let's do it. Let's go find it. Fluid mechanics. But yeah, Femvox. This is the book I like. I like this for physics. I think this is a pretty good one. All right, let's find. Where is Kudu? Okay. And then fluid mechanics question 20.
Yeah.
Okay. Okay. There we go. Okay, it says water emerges straight down from a faucet with a 2.16 centimeter diameter at a speed of that. Because of the construction of the faucet, there is no variation in speed across the stream. What is the diameter of the stream? 0.2 meters below the faucet. Neglect any effects due to surface tension. Okay. So it's got to spread out, I guess, at some point. Oh, I think this is kinematics. I think you have to think about how gravity is going to change the speed, right? Oh. This is kind of a cool question. Okay. Okay, so you have faucet here. And that is, let's just say R is equal to 1.08 times 10 to the minus 2. Yeah? Meters. And then the water's flowing out. And we're looking at what the diameter of the water is here, right? So at the top portion, that's the radius, and the velocity is equal to 3.23 meters per second. But then we go down 0.2 meters. And 0.2 meters below the faucet, now gravity has had some time to work on the water, and it's going to increase the speed of this water. Okay?
Wait, doesn't it say there's no variation in speed across the stream?
No variation in I think they mean across this way. I think they mean horizontally.
Oh, okay.
Yeah. Vertically, there's definitely gravity definitely affects the speed of the stream vertically. Yeah, it has to.
Okay.
Yeah. When they say across the stream, they don't mean like downstream. They mean like horizontally across the stream.
Okay, I see.
Oh, okay. So how do you figure out what the velocity of something is going to be here if you have just the distance? Do you remember which equation we use for that? It's one of the kinematic ones.
Is it it's like initial velocity times t plus 1/2 at squared?
So that would work if we had the time, right? So here, let me pull up. This is totally cool. Let me pull up the kinematics equations. Sometimes they call it like SUVAT. But here we go. And this is why, again, physics builds on itself. We have to remember a little bit from mechanics before. So these are the major ones. I don't really use. You don't really need which one? You don't really need these ones. Yeah, you don't really need this.
Oh, so it's the third one?
It's the third one, yeah. This is called the timeless equation because you see how there's no time involved?
Yeah.
Yeah, so we probably want to use this one. So, we want to figure out what the velocity is down here. So we're going to say, okay, so v squared is equal to v naught squared. V naught was 3.23. And then plus 2 times the acceleration. The acceleration is technically negative 9.8. But then also the displacement is also negative 0.2. And if you want like a sanity check, right, you should know that this velocity should be bigger than what this is. So you don't want this to be a minus sign. You want these two minus signs to cancel each other out. Okay, so 3.23 squared plus 2 times 9.8 times 0.2 is that. And then we're going to square root. We're going to get 3.79, okay? Wow, what's up, Sam? 50 months. Whoa, that's cool. Do I have a new badge for you, Sam, for 50 months? Oh, okay. V is 3.79. Okay. That's meters per second. And then what do we do after this, Em? Once I have the velocity here?
And then you just do A1 V1 equals A2 V2.
Perfect. A1 V1 equals A2 V2. I still got a few. Nice, Sam. Sam, I saw your mom at the at Santa Monica Brewworks, dude, for the USA game. I thought that was too funny. I hope she sent you a photo. It was funny. I was like, oh yes, I tutor your kid. Yeah, you heard. Yeah, okay. All right. So And then let's see. This was pi times 1.08 times 10 to the minus 2 squared. And then V1 was 3.23. And then this is going to be equal to... And what they want the diameter. Oh, so they're being kind of mean here. So this is pi times r squared times 3.79. Luckily the pi's cancel at least. That's nice. I don't even have to deal with that. Okay. So then 3.23 divided by 3.79 times 1.08. Insert. Oh, no. E to the negative 2 squared. Okay, and then we're going to take the square root of that. And that's going to be the radius. But then we need to multiply that by 2 to get to the diameter. Okay. So, it should be basically 2 centimeters, I think. Let me see if that's correct.
I think the numbers are actually like different for mine, but like that makes sense. Yeah.
Okay. Oh, I see. Each student sees their own random numbers. Uh-huh. Let me see. 1 sec. 1.02. Yeah, this random number thing is interesting now. Because now I see a number in this one. This is such a bug. Such so buggy, man. Because on my instructor view, I see a number for this one, but I don't think this number is correct. But in this one has random numbers in it, and this one I don't see a number. So there's something weird. There's something weird with the numerical questions where like numbers are randomly generated. I think sometimes aren't displaying correctly. Because here, let me put that in for my student version. That was question 20, right?
Yeah, so it won't mark the answer correctly?
It might not. Let's just see. I'm curious. I'm gonna yell. I'm gonna go yell at some people a lot. Not do me any favors here. This was fluid mechanics, right? Oh, here, and you need an extension on this, right? Is that what you said?
Yeah, in
Here,
my email.
Yeah, you're good. Let me do it. Let me see if I can do that for you right now, actually. That's the due dates. Manage due date. Homework. Advanced options. 1 sec. Add extension group. And then Emily, maybe?
Yeah.
Oh. Let me see. Cool. All right, great. And then here, let me extend this to... I'll give you till Wednesday. Is that cool?
Yeah, that sounds great. Thank you so much.
I'm gonna do Wednesday. Well, tell me if it comes up for you. Display. Okay, let's see. First homework extension. Okay. Okay. See if that shows up for you. I'm curious because this is the first time I've done extensions on this new platform. So if you like go in and out, it should show you that the homework has an extension on it. Or I hope it does.
It should say it's due on July 1st.
Yes.
Okay, yeah.
It does?
It does. Yeah, it works now.
Wow. Okay, great.
Okay.
Cool. Thanks for beta testing that with me.
Yeah.
Let's see if I get extensions to work. All right. Okay, but then I want to see if I can get the right answer with this one. Oh, okay. Let me see. Let's see if the gravity way was the way to do it. Yeah, okay, cool. Yeah. Okay. So we're doing it the correct way.
Oh, so it marks the answer correctly.
It
And
marks
I-
it correctly. I think it does. Yeah. You should. I actually can't see it on my side because for my account, like the homework's already due or something. But on your side, can you put in new numbers? Will it let you do that?
Yeah, should I just enter a wrong answer?
Oh no.
See?
Yeah, we'll try to solve. Here, let's get your numbers. What's your diameter and what's your speed?
Okay, the faucet's diameter is 1.74 centimeters,
Mm-hmm.
and the speed is 5.07, and it's still 0.2 meters below.
Yeah. The 0.2 doesn't change. Yeah. Okay, 1 sec. So in that case, let me see. 1.74 and 5.07.
Yeah.
Okay, 5.07. Okay. So then this be 1.74 times 10 to the minus 2. But then divided by 2. And then this would be 5.07. I want to see if we just get the right numbers. And then this would be 5.07. Okay, so calculator. 5.07 squared plus 2 times 9.8 times 0.2 square root of that. So we should get 5.44 meters per second. Okay, and then okay. So 5.44, and this is 1.74 times 10 to the minus 2 divided by 2. This is 5.07. Pi's cancel, so we should just be able to get this. So 1.74 e to the minus 2 divided by 2 squared times 5.07 divided by 5.44 and square rooted. And that's going to be our radius. And then we're going to multiply that by 2. We should get 1.67 centimeters. Is I think what I got? Yeah.
Yeah, that's what I got too.
Cool. If you put that in, do you get the right answer? Does it say yes?
I'll put it in now.
Yeah, let's go see. Curious.
Okay, yeah, it says it's correct.
Yay. Something
Yeah.
works today. I'm so happy.
Yeah.
Okay,
Glad the
but
extension works.
yes, I'm glad the extension works. I'm glad your homework question works. I guess multiple parts with random variables don't work.
Yeah, I guess like maybe for the answer key, like it's just wrong.
Yeah, I think it's just wrong. On that part B one with the baby or something, yeah, that one's just wrong.
Yeah. Also, like just curious, do you
What's up?
use like an iPad to like annotate or?
I use a little tablet. I use one of these.
Oh, cool.
It's like a Wacom. Yes, that's how I write.
All right. Well, thank you for the extension and thank you for explaining.
Okay. You're very welcome, Emily. Yeah. Anytime you have questions, come on by. And then, I know the due dates and stuff are like kind of hard, but try to figure that out, because I can do like extensions on the first couple, maybe, but after that, then it becomes like a mess. So, you'll get the hang of it. Just put things in your calendar and you'll figure it out.
Yeah, I'll make sure like it doesn't happen again.
Okay, you're good, Emily.
Yeah.
You're good. Okay. Enjoy.
Thank you.
You're welcome. Bresco says, I theorize if I start spamming 6-7, people will stop thinking I'm Unk. Too funny, dude. I tab back in just to spam that. Oh, man. Okay. Cool. Well, we've been on for an hour already, so here, I'll take this off. And then I'll open the Discord so we can hang out on there. But wow, yeah, we took actually the whole hour to help out students. Isn't that crazy how that changes so fast? All right, let me pop this out. Okay, there we go. And we're back. Ugh. I don't know if that works. Yeah, there we go. Okay. Let's see. Questions. All right. Okay. Let's see. What other questions got submitted today? One from Hypersonic. Oh man, what is this? Hypersonic, what'd you give me here, dude? The Schwartzian derivative? Excuse me? The what? The what is this? Oh, Marcus, this is one we're doing. Use the Schwartz, Luke. Yo, when is that coming out? Are they doing a remake of Spaceballs? Pretty sure they are. Okay, if f is 3 times differentiable and f prime of x does not equal 0, the Schwarzian derivative of x is defined to be the third derivative over the first derivative minus 3/2 of the second derivative over the first derivative squared. Show that the derivative of f composed on g is the same thing as the derivative of f composed on g times g prime squared plus the derivative of g. Oh no, sorry, the Schwarzian derivative of f composed g. Oh. Okay. If I just do the first derivative, right? Let's say let's call some other operator here. I don't know. Let's call like u. Let's say u of f of x is just equal to f prime of x. Then what would u of f composed on g be? I think that would be it's like df dg times dg dx, right? How do you write that? And you can say this. Right? That's just a chain rule. But then, oh man, if you have a higher derivative, now that's a product rule, no? And then the third derivative is even crazier. Yeah. Let's see. We can get chat to teach us. Chat, time to teach me. Teach me about Schwartzian derivatives. First, compute the derivative of h. Okay, so... Yeah, see? Yeah, and then it's a... And then it's a... Oh, man. Okay. So I was actually kind of right here. So if u is equal to f of x, if u f of x is just f prime, I see. You write this. You say it's equal to f prime of g of x times g prime of x. Which I guess they called that h, is what they did, right? Yeah, okay. Okay. So let's say h is equal to f composed of g of x, right? Okay, so then let's calculate what h prime of x would be. That would be derivative of the first at g of x. And then the chain rule would then be times g prime of x. Okay. But then the second derivative, okay, so now that's the derivative of this, which is going to be f double prime g of x at g of x times g prime of x times g prime of x again, plus the derivative of this one, which is g double prime of x times f prime at g of x. Okay. And then if you had a third derivative, oh man, this is a mess. Oh man, now I got a triple product rule, right? Oh. Ooh, why you hurt me so? Okay, so this is f triple prime g of x times g prime of x times g prime of x times g prime of x. Okay, and then plus the derivative of this thing times that, plus derivative of this thing times that, so that's 2. So plus 2 g double prime of x. I think, yeah. And then it's going to be g prime of x, f double prime at g of x. And then this, so then that's g triple prime of x, f prime g of x, plus g double prime of x f double prime at g of x times g prime of x. Oh man. That's just a huge headache. Let me see if we got the same things as they did. Let's see. All right. F prime g of x, g prime of x, cool. F double prime at g of x, g prime of x squared. Okay, yeah, because we got two of them there. And then F prime g of x, g double prime of x, cool. And then here you end up getting F triple prime g prime of x cubed. Oh, I see. And then this one and this one are the same. So there's actually three of them. Yeah, I haven't seen that many tick marks since my last camping trip. What's up, Mr. Aegis? What's up? Yo, Aegis, when's your next podcast stream that you do? You're always interviewing like cool people. Let me know when your next one is. I think you did it like every couple of Fridays or something. Or was it like once a month? Okay. Alright, so yeah, these two would combine. That's where we get the 3. And then this one came down here. Okay. And then they divide by... Oh. Then divide by h prime. So divide by f prime g over g prime. Let me see. Notice how they just start dropping the g prime of x's. So yeah, that's f triple prime. Oh, I see. Oh, an astrophysics streamer. Very cool. Do I know them? What's their channel? And then squaring that? Oh my gosh, dude. What's up, Devious, dude? What's up, dude? Sizzle Galtaire? Wow, this is kind of a cool name. How do you submit questions? Devious, bro, how long have you been in my Discord, dude? You know how to submit questions. That's how you do it. I'm gonna find this Twitch account. Oh, he's a physics VTuber. Oh, I am following them though. Yeah, it looks like I'm already following. Yeah, Syzygy. Yes, actually, I know Syzygy. I've rated their channel a couple times. Yeah, very cool. Anyways, yeah, this is just a mess of algebra. There are some cool things though. Here, I'll point out the things I think are cool. What's up, 5K? Why use AI? Just to kind of double check what we're doing is correct. Like, I didn't want to like have to go through all this and then figure out this was like wrong. But okay, so once you have this mess of h triple prime and you divide it by h prime, right? Remember h prime was equal to f prime at g of x times g prime of x. Okay. You can actually start to group some of these things. So here you can group this together. And so this is f triple prime at g of x over f prime at g of x. And then it's g prime to the third, g prime of x cubed, over just g prime of x. Okay, well this simplifies to g prime of x squared. And then this is the same thing as f composed on g, but in this case it's f triple prime over f single prime composed on g of x, or just on g. Actually, how do we write that? Yeah, we just said on g, and that's like of x, and then it was g prime of x squared. All right, and that's how they got here. Notice how, yeah, they're dropping all the arguments. I see. And then this one becomes f double prime over f prime composed with g. And then there's a g double prime. Okay, because these cancel. Cool. And then this is just g triple prime over g prime. Okay. So that's what this is, at least. And then you can do this one, I think, maybe. Right, because then you have to do f double prime over f, or you have to do h double prime over h prime, which that's the next one. That's what this one was. But then they want that one squared times 3/2, and then this one as well. Yeah, okay. And then it's just a mess of algebra is what it is. Notice the middle terms cancel. Do they? I see 3/2. Oh, I see. 3/2 times 2 gets you 3, which gets you this one. Uh-huh. Okay. So then you're left with that. And that's the first bracket is exactly df composed with g. Uh-huh. Wow. Okay. Okay, cool. All right, cool question, Hypersonic. I don't know if I could do part B as well. Man, what even class is this, dude? Just a bunch of like brutal derivatives. Okay, homework is done. That was seen as a difficulty 9 out of 10 question, by the way. Wow. Here, and I'll share the ChatGPT so you can, if you want to go through all the algebra. Teach second order linear differential equations. If you submit a question, I'll try and do it.
I agree with him, actually.
Yeah.
It's a good idea. It's a good idea.
Well, let's see. We got 3 questions in the queue. We got this. Is this you, Breasticles? Is this second order? I think it's the second order.
Yeah, it's the wave equation.
Okay, let's see if yours gets picked. Let's see. I haven't spun the wheel for a bit.
Let's go gambling!
You did get picked. All right, let's see. Is this part of your summer class you're taking, Breasticles?
I forgot I was muted.
You're okay.
Yeah,
You're
it's,
okay.
it's a wave equation, the second order.
Okay, so
it kind of is. I took it from my notes, but I already knew how to solve it prior to taking the course.
Oh, this. Oh, yeah. This is
Unfortunately, there's,
literally what I did in my class. I love all your commentary during my lectures. They're hilarious. I'm just like,
Oh, yeah.
I'm looking at it. I'm just going. This is so fucking funny. Oh man. Okay, I see. This is the wave equation. Yeah. Yeah, we literally did this today. Well, I didn't solve it. I just showed like kind of the back of the hand little like bullshit derivation they do for it.
Yeah, the cheat coded like, oh well, you can use this sign and see it works.
Yeah, no, yeah. They
Don't
literally just did.
question it.
They did this divided by this, and they're like, oh look, that's exactly 1 over v squared or something, and you're like, oh wow. Yeah, we're not actually solving for it.
It's honestly
Okay.
not even like that bad to solve. It's just the theory behind it that
Yeah.
gets people.
Okay. And then there are boundary conditions, right? U of x0 is f of x. U of t x0 is this is g of x?
Yeah, I don't have great handwriting.
Your handwriting,
to say
dude.
the least. Did you see the way how it looked when I wrote Fourier on my last problem that I put in?
No.
Yeah, you should look at the way that I wrote Fourier. It's not
Oh
pretty.
my god. Oh my god, this. Yeah. I feel like you gave up at the end of writing series. You're just like, scribble.
Yeah, I already had a bad habit of not lifting up my pen as I write, and it turns into like a weird cursive. And then when I started writing on the surface, it got even worse because
You're
there's
like,
way less friction
series.
on the surface.
Yeah.
So I don't even all of my X's look like a reverse alpha because I don't pick up the pen when I go do a swoop to go back up to do the cross.
You guys giving me shit for my alphas, dude. You guys giving me shit for this. For my CX.
Yeah, my
Okay.
X's tend to look like just a reverse of that.
Oh, we got some boundary conditions here. So at 0 and at L, it's also equal to 0. Okay, cool.
Yeah.
So-
We're fixing the
Yeah, we're just
rod in place there.
Yeah, we're fixing the endpoints, right? Okay, cool. And then okay. And then what are you supposed to do with this? Am I trying to find an equation of motion? Like a function?
Yeah, we're gonna solve it, and we're gonna use separation of variables here.
All right, let's do it. I'm down. So, I guess I'm gonna move things on each side, right? Maybe.
Not yet. So in PDE, separation of variables is a bit different from an ODE. In
Okay.
ODE, you just move stuff to its own side,
Mm-hmm.
which we'll do after a first step. But we're gonna start by assuming, and this only works with linear ODE or linear PDEs, but we're gonna assume that our function u is of the form x of x, where x is a function of x, and times t of t, where t is a function
Oh,
of t.
yes, I do remember this. Yes. This is like super X.
Yeah, exactly. It's a function,
Okay.
not an actual variable.
So then, partial U, partial T is, is that just this times the derivative of this?
Yeah.
Right, because we assume this is a constant compared to
Mhm.
T, right? So that's this.
Yeah.
And then that's dt of T dt. Okay. And then if I want to take another derivative,
Yeah, you just take another derivative.
okay. So d squared u dt. Oh. Okay. It's just this, no?
Yeah.
Okay. And then it's the same thing for x, I guess, right?
Mhm.
Uh-huh. Okay. Cool. Oh, don't forget the dt squared. There we go. Okay, cool. All right. I agree with that. Sure.
And now we substitute back in.
And now we substitute back in. Oh, I see. So this is going to go here. And then this is going to go here. Okay.
And it's probably easier to move the UXX over to the other side too, so that it's on the right hand side rather, just because whenever I write it, I write UTT minus UXX. But
okay, so then this is equal to a squared, and then that's this, right? Okay. Interesting. And now do I want to try to group things by variables?
Yeah.
So now I want all the x stuff on one side, all the t stuff on the other side, right? So we're going to put that over there. We're going to put this over here.
Yep.
Okay, cool. Okay, and then this is 1 over x of x. Okay. Now, usually I'd want to take like some sort of integral or something, right?
Almost. Also, I would move the a squared over to the other side. It's not a huge deal, but it just makes things slightly easier.
You want to put a squared here? That's fine.
Yeah, it just makes things a bit easier. And then, so what we'll notice here is, see how the left-hand side is a function of t, and the right-hand side is a function of x?
Yeah.
The only way for those to possibly be equal is that we let it be equal to a constant. Because it can't be a function of x or a function of t.
Oh.
The left-hand side is only a function of t. Right-hand side is only a function of x. So we're going to set that equal to a constant, and we're going to call it negative lambda.
This whole thing is equal to a constant?
Yeah, all of it's going to be equal to a constant.
Oh, the whole thing's equal to a constant.
Yeah, so just the entire equation, that's all equal to negative lambda.
Okay, cool.
And then the same thing with the right side as well. That's also equal to negative lambda.
So wait, we just have negative lambda equals... Or we're going to come up with two equations for this. Oh,
Yeah,
I see.
Because
I see.
that we've separated it, we can turn t of t into its own, its own linear second, I guess. Horatio is getting his wish. It's a second order linear ODE that we can solve for, and technically our negative lambda is an eigenvalue.
Okay. So now I'm going to say all of this is equal to negative lambda. And then all of this is also equal to negative lambda. Okay. And then... Okay.
You would move your t of t, your 1 over a squared t of t to the right-hand side, and then you'd move your x of x over to the right-hand side as well. But we can focus on solving t first.
Yeah, let's solve one of these first. So I'm going to say this, right, is equal to negative lambda a squared t of t, right?
Yep.
Usually I would want to like put this over here and put this over here, right? I want like all the big T stuff on one side, all the little T stuff on the other side.
Not necessarily. So this, technically it's an ODE. This is just t double prime plus lambda a squared t equals 0.
Oh, I see what you're saying. I see. Yeah. Okay. Yeah, this is the same thing as big T double prime. Okay. Plus lambda a squared. Just T is equal to 0. And this, okay, we know has a solution of like, sorry, this is effectively omega squared, right?
Almost. So technically what we do is lambda is an eigenvalue. So it could take either, we say lambda equal to 0, lambda equal to negative alpha squared, or lambda equal to alpha squared. To save you the time, lambda equals 0 and lambda equals negative alpha squared, right? When you would either have a ax plus b or and C1 e to the x type form, those result in a trivial solution with our boundary conditions, meaning that C1 and C2 would have to be 0. So our only option is to say that lambda is equal to alpha squared, and then that's when
where does alpha come from?
We're saying that lambda is going to be equal to alpha squared.
But we're just assigning it to just some variable.
Yeah, we're just assigning the variable alpha squared. Instead of writing square root of lambda, we're just saying that lambda is alpha squared.
Okay. Lambda is equal to alpha squared. You guys hate my alphas. Okay. And then I mean I want to use like cosine and stuff for this.
Yeah, it would become a cosine.
Okay. So, T of T, right, is equal to cosine of alpha A?
Alpha A T. Yeah, alpha A T, and then there's also going to be a sine.
Oh, I see. And this is like C1?
Because it's going to be C1 and then C2.
Mm-hmm. Okay. And then I can say the same thing, I guess, for this one, right?
Yeah.
Right, like by same process. X of X. That one's gonna be equal to alpha. Or sorry. It must be a different, it must be like a C3 then, right?
Yeah, it would be a C3.
C3 cosine of alpha T, right?
Mm-hmm.
There's no A in here anymore.
Alpha X, sorry.
Oh, alpha X, sorry. Yeah. Sorry, this is ddx. And then this is plus C4 sine of alpha X. I see. Yeah, and this comes from the traditional, if you have x double prime is equal to omega squared x, right? The solution is x is equal to sine omega t.
It should be negative.
Yeah, sorry, this is negative. So yeah. Plus cosine omega t. Yeah. Right. Yeah. This is the simple solution that you're supposed to kind of like just like have in the back of your head and you kind of remember it. Okay. So that's x of x, that's t of t. And then we want to use these boundary conditions. Is that what we want to use?
Yeah. Mm-hmm.
Interesting, but u is x of x times t of t. Right?
Yeah.
So isn't that's kind of nasty though, right? Isn't that gonna be like a
yeah? Well,
thing?
so we don't need to do that just yet. We don't need to substitute in.
Okay, we don't need to substitute.
Technically, this is what's called it's a Sturm-Liouville problem. And so we just wanna.
Who's this bitch?
Yeah,
Stern
that was
Louisville?
just the names of the people.
Who's this bitch? Stern Louisville. What's up, derivative? Okay.
But yeah, so we wanna plug in our initial conditions for t and our conditions for x to get our constants just straight into our t of t and our x of x.
Oh, okay. So you're not going to combine them yet?
No, not yet.
Okay, cool. All right, so that was our initial conditions. So u of x comma 0. So when t is 0, this one goes away, right?
Mhm.
So u of x comma 0, that's just going to be equal to c1. Just c1, because cosine of 0 is just 1. Okay.
Mhm.
So that's c1 times this, times this whole thing, right?
Yeah, and we could just say x of x.
Okay. Well, I still got 3 things I don't know, right? I don't know C3, I don't know C4, and I don't know C1. Okay. So maybe this... Oh,
It
and
might
then
help to get our terms for x as well, because we also know that when x equals 0, it equals 0, and we know that when x equals L, it equals 0.
Okay, okay. Okay, so I know u
Right,
of
which
0...
means we don't even need to worry about the t. X of x is whenever it's going to be equal to 0. It doesn't matter what t of t is. So we can just solve x of x for when x of x is equal to 0 with our
Wait,
two
wait,
initial
wait.
conditions.
Wait. You said it's equal to 0. Yeah, I don't care what t is. Okay. I see. So that tells me that C3 has to be 0, right? No. Yes. No. Okay.
Yes. Yeah. C3
Yeah.
has to be
U of
0.
0t means this is going to be C3 times 1, right? And then plus 0. Okay, cool. And so then that's times t of t. Whatever.
Mhm.
Okay, but that has to be equal to 0. And I can't have t of t just being equal to 0.
Yeah,
So
because that would
that's
just provide a trivial solution.
That's a trivial solution, right? Exactly. Okay. So C3 is equal to 0. And then we also know that when u is equal to... When x is equal to L... Okay. So then you have C4 sine alpha L. And then t of t is equal to 0. Okay. So that means that, well, I don't want to say C4 is 0, because then x of x is just 0. So
Yeah.
that tells me a restriction on alpha. It tells me that alpha must be equal to pi over L. Right? Yeah. Because then sine of pi is 0. Okay. Okay. So we've got C3. I've got what alpha is. I still don't have anything for C1 and C2 though, no, right?
Not yet, but we can find it now. Because now we know entirely what x of x is.
Oh, okay. Okay, so x of x is now just equal to... Well, actually, but I still don't know what C4 is though, right? Okay. Sine of pi over L times x. But... am I going to use this derivative thing now? U of t is equal to g of x? You think? I have x of x. And then t of t is that. Okay, so let's get what this is. So du dt, in this sense, that would be C1 alpha. Well, we already know what alpha is. So C1 pi over L. What's up, Katsu? Times A. Oh, that's a minus sign. Sine of alpha AT. Yeah, what's up, Katsu? Long time no see, dude. It's cracking. And then this is plus C2. pi over L A cosine of alpha AT. Okay. But I'm saying that when... Oh, wait, and that's just... Yeah. Okay. And at x comma 0, so when t is 0, this goes away. So we're just going to be left with, what is it, C4? Sine of pi over L x times C2 pi over L times A. Yeah, because then this term just goes to 1. Okay, cool. And that's all equal to g of x. Right?
Yes.
Okay. And then u of x comma 0. So that's C4 sine of pi over Lx. Times, where's my t of t? Okay. And then that's just times C1. And then this is equal to f of x. Okay, cool. Am I gonna divide these two by each other or something? To get like what C2 over C1 is?
No, I don't think we need to in this case.
So what do I do now?
Remember correctly. Basically, I also forgot on the pi over L's there should be an n for the eigenvalue. Any specific
yes. Sorry. This is n pi over L. Yeah. Katsu says, what are we doing here? We're doing some second order differential equations, I think is what this is. Okay. Yeah, sorry. There's n's everywhere. My bad. Okay.
And then from there, it's actually pretty simple. Now we can pretty much just substitute in, and turn it into a Fourier series.
Wait, what? Wait, what? Okay, all right. So, u is equal to this. That's my x of x, right?
Yeah.
And then it's times my t of t, which is all of this. Right?
Mm-hmm. And basically the idea is that we look and we notice, okay,
this is f of x, right?
Of n. And so basically what we can say is, right, it's u sub n, right? And so if you look at it, that looks a lot like a Fourier series, because we have our cosine and our sine terms, and then our m pi over l's. We can say, okay, well, let's take the superposition of all these, because that's all going to be a solution of it, and the sum of any solutions to a linear PDE is another solution to the PDE. So we can say our general solution is going to be the sum of all those, and then we're going to say that C4 times C1 is going to be our A of n, and then our C4 times C2 is going to be our B of n.
Okay. But then, is A of n equal to f of x? Because that's where my C4 and C1 comes in.
Yeah, and so like if we had more specific like values and functions for what f of x and g of x were and all that, we could actually solve for what the Fourier coefficients would be in that case.
Right.
And
Okay.
what our f of x and all that would be. But since we don't have that, we just call it our A of n and our B of n.
Okay. Yeah, that last part at the end is just like, yeah. I see it. I see how this looks like a Fourier thing. It's n pi x over L. Okay. So what do we do next? Are we done?
Yeah, pretty much. You just say AN, BN, and write a summation on it.
Okay, cool.
Technically, we could show that like these are all eigenfunctions and some other stuff, but we don't need to do that necessarily.
We're just gonna call it what it is. It was fun. I've seen this a couple times before, this separation of variables thing.
Well done! Well done!
And I did like it. It was pretty cool.
It is a very, very useful tool. So
I mean, it was very related to what I was teaching in physics today, like this, except like we didn't do any of the differential equation, the Diffie-Q explanation for it, but yeah.
yeah, it was
That's cool.
up, up, down, down.
Yeah, AB start. You were doing the Konami code. I saw that. He was like up,
Yeah.
up, down, down, AB start. Yeah, that's funny, dude. How many more weeks do you have of your class?
It ends this week, and then that reminds me, I need to email him, and I'm gonna try to do a DIS with him for the next semester, because they
What's DIS?
literally don't directed independent study.
Oh, okay, like a senior thesis.
Because I
type
wanted to, well, because I want to take a like a second semester summer course, and they were offering I think it was like structures and patterns of algebra or some shit like that, and I was gonna take that, and then I went to go like look and register for it, to see if I was gonna be the only person in the class, and they had dropped the course off the schedule.
Oh no!
So now I'm like, I don't have anything else I can take over summer, because they offer like, I think it's like Diffie-Q and linear algebra are the only other like courses they offer, and I've already taken those.
Yeah,
So I need to
we need to
figure
get you to
out
grad
what I
school,
would
dude.
do, and
We need to get you to grad
know.
school. We just gotta get you to grad school, dude. That's what we gotta get you there.
that's the hope. I'm kind of already there. Ish.
You're beyond my math levels, dude.
Oh, I mean, like the course I'm taking is a grad course. It's just like they don't offer enough upper division math courses for me to just like take 3 or 4 upper division math courses
Right.
in one semester and get straight to grad school.
Yeah.
Because even like I'm in intro to analysis next semester, and I'm literally the only person registered for that course right now.
Wow. Are there any
Yeah.
math grad students at your college?
I'm not sure. Technically, there's 4 grad students that are in the course that I'm taking now. That being said, I don't think they're real, because I'm the only person that ever shows up to class, and I don't know how the hell they're looking at like the video lectures that he's posting online, because he hasn't posted like notes or videos for like 2 weeks. So
Oh man, dude.
I'm like, these guys can't be real.
That's actually a problem in the U.S. is people signing up for like fake courses just so that they can get like visas and stuff.
Yeah, I don't even. So like,
Although I don't know who's like
what
signing
they're
up for like an advanced like math analysis class or something to like get a visa.
I got no clue, but I haven't seen or heard anything from them. So
And you're literally the only person that shows up to class.
yeah,
That's fucking.
I
hilarious.
sit there and it's just like me. And then the worst part is like right now we're going over PDEs,
Mhm.
so he still has to like teach it for everyone else
Who isn't there?
because they haven't taken PDE, and then I'm sitting there like, okay, dude, like this
Yeah,
shit kind of bores me.
you're-
I've already
You're in like the
taken
cuck
PDE.
chair, dude. You're just like sitting there on the side of the room, just like, are you sure this is okay? Oh my god, dude, that's too funny. All right, we got a couple minutes left. Let me spin the wheel one more time and see who we're gonna get. Is it gonna be Eric
Let's go
or Gladiator
gambling!
Doritos? Who's it gonna be? You won Devious, dude. Where's Dr. Devious? Fill in the graph. Oh. This is chill. Super chill. Let me see. Okay, cool. This is an already factored polynomial. And we have like multiplicities and things. Okay, cool. Degree. So I believe this is like to the power of 1. So this is going to be a degree 6. polynomial. Sign of the leading coefficient. Oh, okay. Well, you have a minus sign. So yeah, it should be minus. X-intercepts. That's wherever these things turn to 0. So that happens at x is equal to -3, x is equal to 2, x is equal to -1. Then y-intercept, that you just plug in 0 and see what you get. So y-intercept, that's 0, comma, and what? That's 3. -3 times -8. So 24. 24 times 1 is just, yeah, 24. Monkey Man says, my transfer application deadline is tomorrow, and I got to write a statement of purpose and finish my CV. And my parents want you to go to IKEA. That's a lot of things, dude. It's a lot of things. Yeah, I think you were asking about that. Sorry, I was teaching Monkey Man during the morning stream. That's the UCLA class I teach, so I can't give as much outside of UCLA class help for it, but yeah. I think I saw Jeff and Breskles helping you out there in the chat though. But yeah, statement of purpose. Is that like a personal statement, or is it you just declaring like what you want to do? I think a statement of purpose when I applied for the GRFP, that was you had to like basically describe like what research you wanted to do and like why it would be important. But a personal statement is different. Personal statement is kind of this cute little essay you write about yourself to talk about, I don't know, your struggles and like what brought you to this point and lessons you learned. Yeah, but future ambitions, yeah. Yeah, that's more of a, yeah, that's what I would think like statement of purpose is like, what do you want to do at this grad school with this degree? Yeah. Okay, this is degree 6. That means it's even. Oh, so that's just cool. So if something is even, that means it's either up, up, or it's down, down. And because it's negative and it's even, it's down, down. So we already know the end behavior. You're back? Well, here, you can come look at it right now, dude. Here, what you wanted to say something? I saw you were asking to get on the stage. It is recorded, but, you know. I didn't explain that much already. Monkey Man says, it's a why you and why here. Oh, now your parents are home? Okay, that's fine. Yeah. Okay. So, because this is even, and because it's negative, that means the end behavior is this. And so you know it must be doing like something like this and then something like this on the edges. And then you have all these intercepts. So x equals -3. That's one of them. X equals 2 is another one, because that's where this is equal to 0. And then also x equals to -1. And then here's the cool thing. If the power of this is odd, that means it crosses over. So it's going to do something like that. This one's even at -1. So that tells you it bounces off of it. And then actually, we could plot the y-intercept, which is really, really tall. 24? I don't know, it's like way over here probably. And then it's going to cross again at 2, because this is odd. It's going to do like that. I don't know. So where is it greater than 0? No, I have a tablet. I'm not drawing with a mouse. I have a tablet here, Eric. Yeah. Okay, so it's going to be greater than 0 between here and here. So that's from you can say like -3 to -1, but not actually at -3, not actually at -1, and then you would say union also from -1 to +2. And then where is it less than 0? Oh, well, that's -infinity to -3, because that's all this. And then union, you'd say positive 2 to positive infinity. Where the slope is greater than 0? Oh, that's annoying. Oh man, I think you have to take derivatives then, right? Because I don't know when this thing turns over. But okay, here. Domain, negative infinity to infinity. Maxes and mins. We don't use domain format for the intervals. Yeah, I mean, you could say this. This is interval notation is totally fine. I mean, or you could say, sure, I don't know. Is it? It'd be like this. It's another way to write it. I just like interval notation. But then, yeah, these are going to be maxes. And then this is going to be a min. So the maxes are the blue dots. Pink dot's the min. And then where is m equal to 0? Well, I think there's only 3 places that happen. So I think it happens here, here, yeah, and here. Yeah, it happens at all the maxes and mins. My grade 11 teacher told us to use domain and range format for intervals. Yeah, I think either are correct. This is fine. You could say this. Yeah, just say x is contained in here. If you want to figure out where the slope is greater than 0, oh man. I feel like you have to expand this out and then take a derivative. No? Is there an easier way to do that? Because I know there are turning points in between the y-intercepts. In between the x-intercepts. But I don't know. I don't know exactly where they are. Yeah, it's whatever. It's a preference for notation. Whatever your teacher wants. I like interval notation. I think it's super easy to work with. Do we just use the slope formula? No. You have to do derivatives here. I'm pretty sure. Have you done calculus and derivatives yet, Devious? You're on summer break. Oh, okay. Yeah. Yeah, because you'd have to figure out where the slope is equal to 0. Because, I mean, here's what I can say. The slope
you may be able to just take a sort of hope and pray guess at halfway between the intercepts.
No.
You
can't do
that. It's not a very... It's not mathematically rigorous, but...
Yeah. I mean, I agree.
Hope and pray.
It's increasing up to here. And then it's increasing here. And then here it's decreasing. And then here it's decreasing. I guess technically, I think it's neither increasing or decreasing here. No. Well, yeah. Yeah. Not mathematically rigorous is an understatement. Yeah. Yeah, Femvox, yeah. Yeah, I think to do this, I think you have to expand this out. Kind of a pain in the ass, honestly. And then you have to take a derivative for it and hope it. Here, let's Let's ask ChatGPT. I'm curious. I'm pretty sure you have to
Product
take.
rule wouldn't be that
It
terrible.
wouldn't be awful.
It's just a triple product rule, but it's not even like that much of a chain rule because all the functions on the inside are
Yeah.
linear.
No, you're not cooked. It's just I'm trying to see if there's an easier way to do it. I know how to. I know the hard way to do it. I'm asking AI if there's an easier way. If this is advanced functions where I have questions like this, he said skip over it until you learn calculus. Yeah. Yeah. Yeah, I want to see if there's a way to do this without using calculus. I don't think there is. Yeah. Instead of expanding the whole thing, use the product rule. Uh-huh. So, set each factor equal to 0. Right, so the one at 2 is obviously equal to 0. And the one at -1 is also equal to 0? Is that true? Oh, yeah, okay. Right, yeah. So, yeah, this one is kind of like the saddle point. That one's that. But, yeah, these are the ones that are tricky. It's these ones that kind of suck. I guess that comes from factoring this out, this quadratic. So yeah, the 6x squared plus 13x minus 5. Uh-huh. Okay. Yeah, but yeah, you do need to use calculus, Dr. Devious. You just estimate? Oh, okay, cool. Okay. So that is the not mathematically rigorous thing that Brescals was talking about. Yeah. So it's increasing from like negative infinity up to like, I don't know, negative 2.5-ish, right? Or negative 2-ish. Ish. And then you could also say from here, from -1 to somewhere in between here. I don't know, like 1-ish. And then it's decreasing from like -2-ish to -1. And then from like 1-ish to 2, and then 2 to infinity. Yeah. Quadratic is a parabola part. I mean, a quadratic is a parabola. This doesn't really have like a parabola part per se. I mean, if you're trying to say like these are parabolas, kind of, I guess, but it's kind of hard to weird. It's weird to talk about like that way. I think Brescals was right. If you have negative x plus 3 here, times x minus 2 cubed, times x plus 1 squared, you could do it as a product rule. This is f of x. So f prime of x is going to be the derivative of this one times everything. So that's just 1. So x minus 2 cubed, x plus 1 squared. And then we would say like plus the derivative. Oh, I see. Wait a minute. Then this becomes 3 x minus 2 squared. X plus 3, x plus 1. All the advanced function teachers are too lazy to take out of these worksheets. Yeah, you need to take it out. And then what is this? Plus 2 x plus 1?
It should be x plus 1 squared.
Yes, correct. Yep, you're correct. And then this is x plus 3, x minus 2 cubed. Bro, what? And then how are you supposed to factor in all this? Yeah, I don't really see that. Instead of expanding, use the product rule shortcut. The derivative factors nicely as this. Dude, where? How did they get that? I don't believe this. This step to this step is just like kind of like, excuse me.
Oh my god, bro. Oh, hell no, man. What the fuck, man? Get your ass on.
Some common factors to all three terms. Okay. I see there's an x minus 2. So here, whatever, let's just pull the negatives out. So we'll just say negative. So you have x minus 2 squared at least, right? And then that's x plus 1. Oh, and there's an x plus 1 in all of them, right? X plus 1, x plus 1, x plus 1. Oh, I see. Okay. And so then this is times x minus 2, x plus 1, right? And then that's going to be plus x plus 3, x plus 1. And you say, and sorry, there was a 3 there. And then that's plus 2, x plus 3, x minus 2. Got you. Yeah, okay. And then this whole thing, I think, eventually turns into the 6x squared plus 13x minus 5. Yeah, okay. So, yeah, don't worry about this stuff.
You done messed up, Aaron.
You'd have to do this, and yeah, you don't know that yet, but the important stuff, you should be able to look at this and see like what the multiplicities are, what the x-intercepts are, and then how that acts on a graph with like bouncing and stuff. Yeah, cool. Okay. I have a video on this one too, actually.
Well done! Well done!
It is cool how it factors there. But yeah, they won't give you derivatives. Yeah, so let me find the YouTube video for that. Where is it? I think it was graphing factored form. Yeah, here, how to graph polynomials in factored form. Here's how to graph polynomials. You should look at this one. This video describes all the stuff about the multiplicities and all the roots. Go watch this video. It's great. It's excellent. Yeah. Fluffy says, "Hey, actual, I'm trying the GRE math subject test again this year. Any good resources to check out or ways to prepare other than to do all of Stewart Calculus 1, 2, and 3? Oh man. Do they have practice exams? I mean, so I took the GRE physics subject test in order to get into grad school, and that's a very, very difficult exam. But luckily, they had a lot of practice ones you could run through. Yeah, definitely run through the practice one. I haven't taken the GRE subject math. I know the GRE subject physics is like a nightmare, though. They're not official. I would still take them. Yeah. I don't know, maybe someone, Zach would know because he went to grad school for math. I wonder if they require it for... Yeah, again, here's a good question, Fluffy. Why are you taking it? I don't even know if grad schools for math require you to take the GRE math. Yeah, Femvox says there's tons of stuff on the math GRE not covered in Stewart. Yeah. Wow. Well, that's cool. 1K. Yeah. I'm glad. I'm glad that video helped you out. Okay. I'll run through some more questions. I'm technically out of time, but you guys are here. I'll do them. Let's choose another winner.
Let's go gambling.
It's Gladiator. It's you, dog. Ooh. Minimize the fold. Calculus you're bad at. Oh, wait, why is the Q showing up? One sec. Go away, Q. I don't know how that got. There we go. Okay, cool. Fluffy says, actually, I want to try for a math PhD. Not all programs require, but some do. I really don't want to depend on my, right, your cumulative GPA because it's like 3.58. And that's not competitive. Yeah, so, yeah, GPA, a 3.5 is still fine. You're above, like, the minimum, which I think for grad school is sometimes, like, 3.5. You're above 3.5, which is fine. The thing that really helped me getting into grad school was talking with professors that were at the grad schools I wanted to go to and trying to, like, see what type of research they did and I guess kind of reading their papers and seeing if it's something that you could help out with. But, yeah, I agree having a strong GRE score can also help because you need something to kind of distinguish you. But ask Zach, Fluffy, you know Zach, right? Zach's been to math grad school, so he would know more about that process. Either two, yeah, Zach's great. Go say hi to Zach about it. I actually have a paper I'm working on group theory dynamics, but whenever I talk to profs, they say that's great, but I'm not on the committee, so I don't have a say. The committee changes every year, by the way, too. But also, the professors can, like, put a request in on the committee to be like, hey, is this student applying? Can you, like, maybe, like, give them a little bit of a bump? They definitely have a say. They have some sort of say. They don't have no say. That's just them being, they're just copping out there. But yeah, I've heard Stewart's good for calculus. I don't even know, like, what do they test on the math? Is it the same as, like, the AP exam? Is it just derivatives and integrals? Maybe some multivariable stuff, probably. Oh, do I just email them? Yeah, the problem is that, like, email is... dude, as evidence... Dude, I have so many emails I need to answer for my class. Yeah. You're in Latin America, so I get it. So it's kind of hard. And you're applying to American schools, I guess, right? Yeah. You can try emailing, but I know a lot of professors don't really respond to email. Because they get so many of them. I'll fly out. I'm willing to do anything. This is my dream. Oh, Fluffy.
Good job.
Oh, man. Yeah, I'm just such a fan of, like, meeting people in person. And, like, I think in-person connections are such a valuable thing these days. Especially in a day where everything's online. Like, you really stand out if people know you in person. But... yeah, I also don't want to tell you that you have to, like, get on a plane and go schmooze and stuff. I think also emailing professors and, like, asking for advice. Professors love to give advice. So if you ask some advice on, like, hey, you know, what openings do you think I should, like, pursue or something? Does it help if I go to an open math conference and shoot my shot? Yes. Yes, conferences are great. You want FaceTime, man. That's what you want. You want people to, like, to know who you are and, like, have some, like, face-to-face. So you're not just, like, another name on an application. That's how at least I got into grad school. Slide into their DMs. It's another funny one. Yeah, math conferences are great. Yeah, getting some sort of, like, face-to-face interaction is really, really helpful. Asking good questions, you know, at their poster sessions or at their, you know, whatever. And, like, seeing if you can, like, contribute. Doctorates and masters. Yeah. Yeah, you could also just get a super good score on the GRE, sure. And then that would make you stand out as well. I think doing research, I mean, you said you're putting a paper out. That's great. Stuff like that should really help. All right, here. Let me see this question for gladiators. Yeah, and you can take it a bunch of times because I think you only submit your best score. One corner of a strip of 8 centimeters wide is folded so that it lies along the opposite edge. See the following figure. Find the least possible length for the fold line. Oh, okay. This is the fold line? Okay. Well, you have to come up with an equation. All right, so let's see. All right, if this is A. I think what we're going to do is we're going to vary, like, where along here. So here, this is going to be my variable. I'm going to call this X. X is how far from the end of the paper I decide to, like, put the corner. No. Really? Integrals make you... Look at the integral a day stuff. That Instagram is great. They have a lot of really cool techniques for that, too. I think integrals are fun, like little puzzles. Okay, if that's X... This is A. How can we describe this stuff? Let me think. How big is the fold line? Yeah. I get it. I was the same thing with like sine and cosine. Sine and cosine usage just like freak me out. Wait a minute. If we take this piece of paper and we fold it over here, this length plus this length has to be equal to A. Oh, this is kind of cool. Right? Because this and this were all part of this side. Okay, I think I'm getting somewhere a little closer. Here, let me call this like Y. And so then this is equal to A minus Y. Yeah. So this is A minus Y. Okay, cool. I just tried this fold problem for a bit, but couldn't crack it. I think I might have messed up somewhere. Yeah, this is a fun one. Gladiator, where'd you find this question, dude? Is this one of these, like, Kaylee questions or something? I feel like it should be simple. Okay. I know that this length is also equal to this length, right? This is a regular ass calculus question? No way. This is a tricky one. We can also draw another auxiliary line, can't we? Because then this is equal to z minus x. When will the next chess tournament be? Probably next week. I just got back. I literally got back this morning at 9. I had a 6 a.m. flight from Chicago. I was kind of tired. Really tired today. Teaching. Alright, that's z minus x. That's z. this is still A, right? Yeah, it was kind of a vacation, I guess. So A squared plus Z minus X squared is equal to Z squared. That's from this, yeah? Oh, okay, wait. And then Z squared plus A minus Y squared. That's equal to the fold squared. The key thing here is, yeah, if we're going to do something with calculus, we need this thing to be a function of just one variable, which we almost have it. And I'm starting to see, like, here, like, this is a triangle, right? This is another triangle. This is another right triangle. And I think with all of those, we can figure something out. Yeah, A is constant. Correct, actually. Yeah. So wait, what's the other one we have? We have X squared plus Y squared is equal to A minus Y squared. Ooh. Oh, man. So wait, that could be substituted with that. Isn't that diagonal on the fold equal to Z? You think this is also equal to Z? No, I don't think so. I agree this is equal to this, right? Because we folded this up. And then, like, this side folded up here. But I don't think this is a right angle per se, right? Do Pythagoras. Yeah, so I did Pythagoras for this one. I did it for this one, and I did it for this one. That's the hypotenuse where one is a minus y. Oh, where one is a minus y, the other one is z. Your opposite is a minus y, and your adjacent is z. Oh, are you saying from here? Yeah, fold squared is z squared plus a minus y squared. I agree with that. Yep. That's this. Yeah, I got that one. Yeah, that's this one, right? And then this one is here. No, you're not dumb. It's okay. And then this one's here. Okay, so we have... Okay, fold is a function of... you're right. A is a constant. So I need some function that relates y and z, like, strictly. Z squared equals a squared plus z minus x squared. Yep, I agree with that. Yep, that's this one. I'm tempted to just, like, plug this in for here. No, because then I get z squared plus x squared plus y squared. Those are all different things. What's up, Pineapple? There's one more relationship I can see, which is a x over a. Yeah, I feel it, right? X over a is equal to a minus y over z. X over a Oh, okay. Maybe. Wait. Are you seeing like some inscribed triangle thing? Sorry. X over A. X over A. A minus Y over Z. Where are you getting that from? Are you saying that this triangle and this triangle are the same? You can draw from the bottom right corner to where the corner lands after the fold. Then that line will be perpendicular to the fold. Okay. So you're saying this is also? Oh, okay. Okay. So then you have this triangle is inscribed in this one, I guess, right? So x squared is equal to a squared minus 2ay. From here. Yeah, I agree with that. How long is the video solution, Gladiator? So Femvox says x over a is equal to a minus y over z. 18 minutes? No. Jesus, yeah, let's go look at this question. Sorry. 18-minute solution. Oh God. Yeah, okay. Oh my God, yeah. Yeah, I don't think this was gonna happen. Try and work it out tomorrow? Yeah, cool. Alright, yeah. In the interest of time. I don't think I can do this one. We were getting close. But here, yeah. I'll post that link in there as well. It is a great problem. Yeah, pretty cool. Difficulty 8 out of 10, though, is what they said. Well, here, we'll post this link there for people to see it. Yeah, if you work it out, do it on the Discord. Yeah, appreciate that. Yeah, I put the... It's in the post here, yeah. So there's Gladiator's question. There's our attempt at kind of working on it, and then there's a solution as well. That means 2 out of 10 for you.
Disqualified.
I don't know, stuff where like I have to draw like auxiliary lines and stuff in geometry.
Oh no.
Disqualified.
I hate those. Okay. One more question from America. We'll do the last one. No, and then I'm gonna go take a nap.
Let's go gambling!
All right, let's see. What do you got for me? Oh, this is good. I like these. These are fun. This is calculus, yeah. Spitting for one person. Hey, it's still a thing. Okay. Water's being drained from a tank. Instant trauma. Oh no, dude. Hey, at least it's not an integral, dude.
What the fuck is this piece of shit?
It's okay. Okay, the volume remaining in the tank is that. Okay. So it is going down, right? As time increases. Find the volume of the water in the tank after 5 minutes. Okay. Well, that's just via 5, right? So 3,000 times 1 minus 5 over 10 squared. And so that's going to be 3,000, 1 minus a half, so that's just going to be 1/2 squared. So that's equal to 3,000 over 4, which is 750 gallons. Yeah. Or liters, I guess, sorry. Okay, cool. Yeah, America, this is yours. So yeah, when they want the water in the tank at 5 minutes, that's all they want. The rate at which water is being drained from the tank. Okay, so rate of draining is going to be technically negative dVdt. Because dVdt, it's going to be negative because the volume is going down. And so the derivative, which is the change, will also be negative. But usually they want the rate of draining to be like a positive thing. So I just put the minus in front of it. Okay, so let's figure out what dVdt is. Okay, so ddt of 3,000, 1 minus t over 10 squared. The nice thing about like a multiplicative constant is you can just like kind of pull that out front. Such a physicist point of view. Yeah, right. Yeah. Okay. So now I need 3,000 times the derivative of 1 minus t over 10 squared. This is going to be a... what's it called? Product rule? Not product rule. Chain rule. So I'm going to be like, well, I don't know what the derivative of 1 minus t over 10, all that squared is, dt. But I do know what the derivative of something to the second power, dt, is. And that's going to end up being 2 times whatever's inside to the first. But then we have to do ddt of what was inside. Yeah. Okay. So this is 2 times 1 minus t over 10 to all to the first. And then the derivative of this, okay, so what's the derivative of 1 minus t to the 10? Well, derivative of 1 is 0. And the derivative of negative t over 10, that's the same thing as negative 1/10 t. And so the derivative of that is just negative 1/10. Because this is just like t to the first, right? The first power comes down, then you get rid of it. Okay, cool. So you're left with dVdt is equal to 2 times 1 minus t over 10 all times negative 1/10. So you can actually like pull this out. So now this is just, and then negative 1/5 1 minus t over 10. You're right, but stop. So many ways to spell your. Okay, so that's dVdt. And then technically we want negative dVdt because we want the rate at which it's decreasing. So that's going to become positive. Okay. And this should make sense, right? Because when t equals 10, the rate at which water is draining is 0. There's no water left. Oh, yeah. Oh, the Nightbot? Yeah. Yeah. It does that because, yeah, I don't know. Most people use the wrong version of your. Okay, so they want it at 3 minutes and 8 minutes. Okay. So, at 3 minutes, that's just dVdt at t is equal to 3. And so, that's going to be 1/5 1 minus 3 over 10. So 1 minus 3 over 10 is 7 over 10, because this is like 10 over 10. And you have 7 over 10 times 1/5. So that's going to be 7 over 50. And that would be liters per minute, right? Because volume was measured in liters and the time was measured in minutes. And then at 8 minutes, you have dV/dt at t is equal to 8. So that's 1/5. 1 minus 8 over 10. So that's 2 over 10. So 2 over 50. So that's 1 over 25 liters per minute. Cool. Does that make sense, America? This was, a little tricky. You had to remember how to do a chain rule for a derivative. Okay, nice. Good job.
Well done! Well done!
All right, let's mark that one as done. Daddy Luigi. Yes, it is recorded on Twitch. Yeah, so everything's also on YouTube. So every time we do a question, it gets posted here, and there's a link for it. So, well, once this is done recording, it'll show the timestamp of it. You've solved your second semester problem? Ooh, nice.
Yeah.
What's the solution?
I am doing a DIS, I think.
Nice.
Good job.
He's got to see your thesis going.
I just have to figure out what I want to do it on, I think.
Okay.
Probably Green's functions. Green's functions would be a fun.
Green's functions are cool.
Summer too. Yeah, like a. Probably just honestly, I might just have him do it over the end of our PDE book on Green's functions. I know there's nonlinear PDEs in there. Fourier transforms, eigenvalue problems, that type of stuff.
Nice.
Because they didn't go super far into the book when I took it. And it'd probably be helpful for him too, because he's teaching PDE this coming semester.
Yeah, so it'd be a little warm up for him.
Yeah, he hasn't taught PDEs before, I don't think. Well, I mean, he knows about it, but normally it's been a different teacher who does a bunch of stuff with PDEs, but he's a department head or some shit now, so he's doing most of that stuff.
He's a politician now.
Disqualified.
All professors
Something
become
like that.
politicians. Yes. Daddy Luigi says, I can get 2 coins. What's this for? Daddy Luigi? What? Yes, you can, Daddy Luigi, but you gotta do it in the right channel. You gotta do that in the extra credit. You gotta do it in referral. That's where you're supposed to do it. Yeah, there you go. Okay. All right. But yeah, I do have to go. But Luigi, if you want us to work on that question next time, come by office hours and make sure you use the website that people are using to submit questions. That's the best way to get your question in the queue. So come by tomorrow's stream. We'll do it. That's the website for it. Okay, cool. All right, let's close out the stream. All right. Thanks again, everyone, for coming to Extra Education Office Hours. Appreciate all of the questions, hanging around. You guys are great. Thank you for all the server boosts. Thanks, Sam, with the 50 months of subscribing. Dude, wow, that's 4 years and 2 months. That's a while. Crazy. Great stream. Appreciate you guys. Yeah, you guys are great. Our next stream will be tomorrow. That's going to be at 6 o'clock Pacific, 7 Mountain, 8 Central, 9 Eastern. And then also I'll be teaching more physics in the afternoon. Penn Center's got some real analysis. And it looks like Zach is on right before us for some math education channel stuff. Yeah. You guys are talking about like Galois theory. I don't even know what Galois theory is. But that's cool. We do have a lot of fun extracurricular study group things that happen. Yeah. I will announce. We'll probably do a chess tournament on Friday. Or we'll do Fortnite. We'll do something. We'll do some games on Friday. Because that's technically also a holiday. And then Penn Center's doing Minecraft dungeons and then Zelda things. Cool. Gawa? Oh, is it not Galois? It's Galwa? Oh, so there you go. That's how much I know of it. Euler? Euler? Alright. Okay. Anyways, yeah. So make sure, come on by tomorrow. We'll do more fun stuff. I'm getting back into the swing of things. I gotta go answer like 50 emails. I have so many emails from this weekend from all my students. But let's go raid someone. Let's go say hi to another streamer. Who do we got? Who's on? Nice. Casey. Let's go say hi to Casey. I like Casey. She's sculpting. It looks like a bird or something. Oh, I don't know what that is. Okay. Cool. All right. Enjoy the start of the week. We'll see you tomorrow. Peace.